Alright, so we're ready for the last worksheet in the class. The worksheet's titled It's the Law, right? So we're going to explore three laws identified of probability in the text, right? So the first law of probability, right? So here we have, so I just want to make a note. So computing probabilities involves careful use of the three laws of probability, right? So here we're given a definition, the first law of probability. So the first law of probability says the probability of event A and event B occurring is the probability of A and B, which is equal to the probability of A times the probability of B given A, right? And if A and B are independent events, then what that means is that the probability of B given A is equal to the probability of B. So in other words, A does not influence B, right? So they're independent. So if that's true, then we have this formula, right? So this is only for independent events, right? So here's some examples. So if we flip two coins, these are considered independent events, right? The probability of the second flip does not depend on the first, right? They don't influence each other. But choosing two committee members are dependent events, right? Because the probability of choosing the second member depends on the first, right? And we're gonna work through an example of that. Right? So applying the first law of probability. So we're given that a subcommittee of two people will be chosen from a group of six: Sue, Ann, Jill, Bob, Jim, and Joe. So the first three are women and the last three are men, right? So just making that obvious. So number one says, what is the sample space for this problem, right? So to get the sample space, we would need to list, Sue, Ann, Jill, and so forth, right? And then across the top, we could list Sue, Ann, and Jill, right? And see the combinations we get, right? But Sue and Sue wouldn't be in our sample space, right? Because we can't choose Sue first and second to be on this committee. So I made a diagram here that's a little more clear than my writing. So we have a table here. So maybe here's the first slot and here's the second slot. Right. So again, the idea is I can't choose Sue for both, right? So that's why this is darked out, right? Same for Ann and Ann, Jill and Jill, Bob and Bob, Jim and Jim, and Joe and Joe, right? All of those go away, right? And if we count here, we have, what, 1, 2, 3, 4, 5. So 5 here, so count how many items are in my sample space. Right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Right, so I get 30 matches, 30 pairs here, right? But something that we have to consider is choosing Ann first and Sue second. Wouldn't that be the same thing as picking Sue first and Ann second, right? Aren't these two things the same? And they are, right? So we end up having double the amount that we actually need, right? So there would only be 15 items in my sample space, right? So we cut out all the doubles, right? So the gray, we could let the gray be my sample space. Right? So we just need half of them. Right? So the sample space would be listing all of those. So one way to list a sample space is you could do an ordered pair of like Sue, comma Ann to denote one, right? And then do another ordered pair. So here, this is who we're choosing. It's just showing the pairs of who we're choosing, right? So there are 15 things total. If you wanted to count how many things there were total, an easy way to do that would be a combination, right? So let me do some erasing here. So remember, we looked at combinations, and combinations are where an order doesn't matter, right? So if I have 6 people and I'm choosing 2 items, right, I can do 6 combination 2, right? So this would be 6 factorial over, so using my equation, 4 factorial times 2 factorial. So this ends up being 6 times 5 times 4 factorial all over 2 factorial. And there's a 4 factorial here, right? So this 4 factorial crosses out with the top and bottom. So what we're left with is 6 times 5, which is 30, divided by 2 factorial, which is just 2. So we get 15. Right? So there are 15 items in my sample space, right? Because order doesn't matter here, right? So we should have 15 things. So number 2, now we're asked to compute the probability the subcommittee will contain two women, right? So we can use the classical definition, right, of probability just by looking at my sample space, right? So the probability of 2 women, right, would be equal to the number of ways that we can get 2 women in my sample space. So if we look above, there are 2 ways, right? We can have Sue and Ann, we can have Sue and Jill, and then we could also have Ann and Jill, right? So there are 3 ways that we could have 2 women. And there are 15 total things in our sample space, right? So again, just look at this table and identify where we have 2 women, right? So Ann and Sue is 2 women, Jill and Sue, and Jill and Ann, right? Those are the only ones that have 2 women. So we have 3 out of 15, right? So this gives me what, 20%. So we take 3 divided by 15, we get 0.2, or 20%. So we can use the classical definition. But we can also use the first law, right? We were asked to use the first law, right? So using the first law, the probability of getting 2 women is the same thing as the probability of the first being a woman and the second being a woman, right? So this is equal to the probability of the first being a woman times the probability of the second being a woman, given that the first is a woman. Right? So just using that equation for my first law. Right? So now we need to find what's the probability of the first being a woman, right? So for the first one being a woman, there are 3 out of 6 ways to choose the first woman, right? There are 3 women and 6 people total, right, that we're choosing. So the probability that the first is a woman is 3 out of 6, right? 50%. So then now we have to think about, well, how many ways are there for the second to be a woman given the first is a woman, right? Well, if the first is a woman, then there's 1 less woman left, right? So this would be 2, right? So for example, if Jill was taken, there'd only be 2 women left to pick from, right? So we have maybe I'll list my people again to make this a little more clear, right? So we have Sue, Ann, Jill, Bob, Jim, and Joe, right? So here's my sample space, right? Here's my box, right? So we're trying to calculate what's the probability that the second will be a woman given the first is a woman, right? So let's assume Sue was the first woman chosen, right? So she's the first woman chosen. So she's now gone, right? So granted that the first was chosen as a woman, we have 2 women left, right? And then how many total options do we have? 5, right? So this would be 3 out of 6 times 2/5, right? So this would end up being 6 out of 30, which is So if we take 6 divided by 30, we get 0.2, right? So 20% still, right? So sometimes maybe drawing a diagram or a visual might help you with the probability, right? We're just using that classical definition of probability to find, you know, what's the probability of the first being a woman, what's the probability of the second being a woman given the first was already a woman, right? Alright, so then on the next page we're given the second law of probability. So the second law of probability deals with an OR, right? And one thing to point out is that in set notation, right, we have two symbols. We have this symbol and this symbol. The one that you can draw a line, a horizontal line to make an A, this is and this one's OR, right? So this symbol is and this symbol is OR, right? So notice these are the same. One is using the words OR and the other is using the symbols, right? So the second law of probability, so we're having event A and event B again, right? So if we're saying the probability of event A or event B occurring, that's equal to the probability of A plus the probability of B minus the probability of A and B, right? So with this rule, what I like to think about are two Venn diagrams, right? So let's say this is event A and this is event B, right? So if we look at the probability of A, that would be all of this, right? Everything that's in circle A. And then when we look at event B happening, that would be all of this, right? Now the problem becomes if we want either one or of them happening, we can't just add those together because then we're doubling, we're counting this twice, right? We're doubling this area, right? We're counting twice. So doubling or counting twice, right, is part of the problem. Because when I count it for, if I include this area for A, I count it once, and then when I include it for B, I count it again, right? So to get rid of that overlap, that's why I have to take this away, right? Because in here, this is A and B, right? A and B. So these are things that are common between A and B, right? Now, sometimes this intersection could be equal to 0, right? So that means that we have disjoint events, right? Meaning they don't overlap. So if we have disjoint events, then this part is 0, so then we get just this equation, right? Alright, so here's an example applying the second law of probability. So we still have the same situation with the subcommittee, and we're asked, what's the probability that at least one man is chosen, right? So again, we could use the classical definition. So the probability of at least one man is chosen. So there are 15 things in my my sample space. And if we look up here, right? So the probability of at least one man would be chosen would be all the cases that we didn't highlight in yellow already, right? Because the place, if you remember right, what I highlighted in yellow, these were the cases where everybody was a woman, right? So everything else would be have at least one man. So it could have one man or two men, right? So we could have, so here's one man, one man, one man, right? One man, one man, one man, and so forth, right? All of these have at least one man. So there's, what, 12, right? So using the classical definition, there are 12 out of 15 ways to have at least one man. So if we simplify this, right, if I take 12 divided by 15, should get 80%, right? 80%. So we get 80%. Right? So then if we apply the second law of probability, so the probability of at least one man, right? What this means logically, right, is that the probability that we have the second person chosen being a man or the second person chosen being a man, right? That's what this means logically. So if I use this equation, right, this would give me that the probability of the first is a man plus the probability that the second is a man, and then I have to subtract off the probability that the first is a man and, right, the second is a man, right, because we don't want to count that twice. So the probability that the first is a man is 3 out of 6. Right? There are 3 men to choose out of 6 people total. Right? The probability that the second is a man is also 3 out of 6. Right? There are 3 ways to choose 6 men. Right? And I need to subtract off the number of cases where we have both being a man, right, first and second. So from our sample space, there were 15 outcomes possible, right? And if we look back up at the table, there are 3 scenarios, 3 spots where we have all being a man, right? We have Jim and Bob, Joe and Bob, and Joe and Jim, right? So this would be 3 out of 15, right? Because again, there are 3 cases out of 15 where we have both being men, right? So then if I do some calculation here, we would have 1 minus 3/15, which is 12/15, which is 80%, right? So we get 80% again. All right, so now we're ready for the next page. So number 4 says compute the probability that the subcommittee contains 1 man and 1 woman using the first law and the second law. All right, so we want to use both. So I like to always start out using the classical definition, right? So we want the one man and 1 woman, right? 1 man and 1 woman, right? So the classical definition, we just look, well, how many times in every sample space does that happen, and we divide by the total number of things in my sample space, right? So there are 15 items in my sample space, and if I look up here, we're looking for how many times do I have a man and 1 woman, right? So that would be all of these cases, right? So there are 9 of those, right? So this would be 9 out of 15, which is what, 60%. So then now let's use the first law and the second law. So the probability of getting the first being a man, oops, didn't mean to put that D, and the probability that the second is a woman, let me before I calculate this, let me do one thing, right? So we have to think about this logically. What does the probability that the first is a man and, or excuse me, not the first. What's the probability of having one man? So having one man and one woman, right? What does that mean? So logically, right? This can mean, right? So this could mean that we could have the probability of the first being a man and the second being a woman, right? Or, right, so that's one case this could happen, right? So if I want one man and one woman in my sample space, the first could be a man and the second could be a woman, or the first could be a woman and the second could be a man, right? So that's one way logically to think about this, how to write this, right? So these are the possible scenarios. So we have to use the first and the second law. So now what we can do is use the second law to split this up, right? So this would be equal to the probability that the first is a man and the second is a woman plus, so this part is like my A, right, event A, and this part's like my B. So remember, we have the probability of A or B is equal to the probability of A plus the probability of B, and then we have to subtract off the probability of A and B, right? So we have the probability the first is a man and the probability the second is a woman. So then we'd have plus the probability that the first is a woman and the second is a man. And then I would have to subtract off the probability that both cases are true, right? So we have to subtract off the probability that the first is a man and second's a woman, and then we'd have oops, didn't mean to put a parenthesis there, and the first is a woman and the second is a man, right? So being able to write that. But if you think about this intersection is going to be 0, right? We can't have the first being a man, the second being a woman, and the first being a woman and the second being a man, right? These are disjoint events. So so this probability is going to be 0. Right? And again, the reason why this makes sense, right? Because if the first person is a man, then that person cannot also be a woman, right? So it's either one or the other, right? So that's why that's just 0. So really what we need to focus on is this part, right? Since these are disjoint events. So now we're going to have to apply the first rule, right? The first law, because this is an and. So the probability that the first is a man and the second is a woman is going to be equal to the probability that the first is a man times the probability that the second is a woman given that the first is a man. Right, we have a conditional probability, so just applying that rule. So the probability that the first is a man is 3 out of 6, right? The probability that the second is a woman given the first is a man, right, would be 3 out of 5, right? So again, the reason why this is a 3 is because there are 3 women left, right? The first person we took out was a woman, right? So that, or excuse me, the first person we took out was a man, so that didn't take away any women, right? So we still have Sue, Ann, and Jill inside, right? So again, here's Sue, Ann, and Jill, and here's Bob, Jim, and Joe, right? So if we select a man, right, we're given that first one's a man, so let's say we select Bob, right? So here's my first man drawn. So then I have 3 women left to choose from out of 5, right? So that's why this becomes 3/5. So if I multiply that together, I get what, 9 out of 30, right? So we're gonna need that, right? So actually, this should not be an equal sign here, right? So I'm calculating each one separate. So that stops my chain being equal, right? So then I found this piece. So now I need to find the probability that the first is a woman and that the second is a man, right? So again, applying that first law. So let me get rid of this. Applying the first law, this would be equal to the probability that the first is a woman times the probability that the second is a man given that the first is a woman, right? So we can calculate this. So the probability that the first is a woman is 3 out of 6, right? There's 3 possible women to choose out of 6 outcomes. So the probability that the second is a man given the first is a woman, right, would be this, right? So again, we're told that the first is a woman, so that takes away one item, right, one person. And since the first was a woman, we still have all 3 men left, so this would be 3. Right, so we get 9 out of 30 again, right? So then the total probability, the probability that we have 1 man and 1 woman, 1 man and 1 woman, right, is equal to, so we would have the sum of these things, right? This 9/30ths and this 9/30ths. So we would take 9 out of 30 plus 9 out of 30, and we get 18 out of 30, right, which reduces down to be what we can say 60%, right? So we found this using the classical definition and by applying these rules, right? And you might wonder, well, Tyler, the classical rule is much easier than trying to apply these laws of probabilities, right? So it's not always possible to list everything in your sample space, right? Your sample space may be too large to list everything, right? So that's why we need these laws, right? So we have one last law to look at. So that's the third law of probability. So the third law of probability says that the probability of event A is 1 minus the probability of its complement, not A, right? So for example, like winning and losing, right? We talked about this in the last video. So this is just putting it more formal, right? And also, if we take this into consideration and assume that we have independent events, then we can apply the first law to this formula, and we get this guy, right? And this is what's called the golden rule of probability, right? So we're going to apply these. So number 5 says we're going to flip 2 coins and determine the probability of getting 2 heads and the probability of getting at least 1 head. Right? So let's find those. So the probability of getting 2 heads is going to use the first law of, and these are going to be independent of one another, right? So the probability of 2 heads is equal to the probability that the first is ahead and the second is ahead, right? That's what that means. Probability of 2 heads means the first is ahead and the second is ahead. So this would be equal to that the probability of event A happening, first head, times the probability that the second is ahead. Right? And again, these are independent events, so we can write it in this way, right? So the probability that the first is ahead is 1/2. The probability the second is ahead is 1/2. So this is 1/4, right? So the probability of getting 2 heads is 1/4. So if you wanted to use the classical definition, you would just have to list all possible outcomes, right? So I could get tail, 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 head. I could get head, head, and head, tail, right? So there's only one guy that gives me 2 heads, right, out of 4. So this is my sample space, right? So there's 1 out of 4 where I get 2 heads, right? So now we're asked, what's the probability of getting at least 1 head, right? So with this, we could use the second law. So the probability of getting at least 1 head is equal to the probability that the first is ahead or that the second is ahead, right? That's what that means. So this would be equal to the probability that the first is ahead plus the probability that the second is ahead. And remember, we have to subtract off the intersection, right? We don't want to count that twice. So I would need to take away the probability that the first is ahead and the second is ahead, right? Because both of those events could happen at the same time, right? So they're not disjoint. So we do need to subtract that off. So the probability that the first is ahead is 1/2, right? The probability the second flip would be ahead is 1/2. So now I need to take away the scenario where I have the first and the second being ahead, right? So we calculated that above and got that to be 1/4, right? So this would be equal to 3/4, right, when we subtract, or 75%, right? So we have a 75% probability of getting at least 1 head, where we have a 25%, right? This is 25% probability of getting 2 heads, right? And then again, this makes sense following the classical definition, right? We can look at the sample space. Another way that we could calculate the probability of at least 1 head would be to apply the third law of probability, right? So that would mean this would be equal to 1 minus the probability of getting 0 heads, right? So that's the complement. So the complement of getting at least 1 head would be 0 heads, or in other words, getting all tails. So this would be 1 minus, so the probability of getting 0 heads would be 1 out of 4, right? That's if you get tail, tail. So only one of those occurs out of 4. So this also gives me 3/4, right? So this was, so first thing we did, we applied the first law, then we applied the second law and the third, right? So we got practice with all of those again. So then now we want to look at applying the golden rule. So it says you are applying to 5 colleges and believe you have a small 10% chance of getting into any one of them. What is the probability of getting into at least one of the schools, right? So one thing that we have to note is that my decisions are going to be independent, right? So we have independence here, right? So I know I have independence because, you know, if I apply to 5 schools, if I if I get into one or the other, that decision doesn't influence the other school of accepting me or denying me, right? So those are independent of each other. Also, if there's a 10% chance of getting into them, that means that there's a 90% chance of not, right? So chance of not getting into them, right? Because that would have to add up to be 100%, right? Either they accept me or they deny me, right? There's no in between. So if we apply the golden rule, right? The probability of at least one acceptance is equal to 1 minus the probability of getting 0 acceptances. Right, so the probability of at least one acceptance, the complement of that, would be getting the probability of 0 acceptances. Right, so this would be equal to 1 minus. So we would have the probability of not getting into school 1, which would be 0.9, and then times the probability of not getting into school 2, and then school 3, and then school 4, and then school 5. Right? So all I'm doing is applying this formula. Right? So you might want to have that on hand, right? So we're just applying this. So I'm plugging those things in. So this would be the same thing as 1 minus 0.9 to the 5th power, right? So if we do this, 1 minus 0.9 to the 5th power, getting roughly 41%, right? So this is equal to 41%. So that's my probability of getting into at least one of the schools, right? All right. So that wraps up this worksheet. So you should be preparing for the final exam. If you have questions, please email me.